So, the transfer function operator form, now it is fairly clear to us how the autoregressive model is born. It is born by assuming that the impulse response decays according to a power law, right. Whether we state it explicitly or not, henceforth you should always assume that the moment you are fitting an autoregressive model to a series, you are implicitly saying that the impulse response for that series, for that process is decaying according to a power law. We will make another statement as a consequence of this using AR model. So, let us move on and discuss the two features of autoregressive models. One is the stationarity aspects, which we have more or less discussed, but I will make a formal statement, and there is something more to discuss about stationarity. And the second aspect is the ACF itself. What, how does the ACF look like? We have seen that earlier, but we will formalize now, we will spend a bit of a time with Yule-walker equations. So, the transfer function operator form is fairly straightforward. It has a denominator form. It is in a rational form, but only the denominator is a polynomial in Q inverse, in contrast to the moving average form. And now, let us turn to stationarity. Again, we have already stated, I am going to skip this formal statement, but let us study an important aspect of stationarity and understand another dimension of this stationarity issue with AR processes. What we are saying is, any ARP process is stationary if and only if the roots of the characteristic equation are outside or inside the unit circle, depending on whether you are looking at Z inverse or Z, in terms of Z inverse or Z. Fine. Does it mean now that any process, for example, if I take a process, an AR process, let us say is 2 Vk is 2 Vk minus 1 plus Ek. This is an AR1 process. Does it mean that this process is non-stationary? Yes or no? Yes, right? I am asking such simple question, you must be thinking there must be a trap somewhere. As per the statement, it is, isn't it? And it is true. If you were to simulate this, you would see an explosion of Vk, it will run away, right. So, it is not stationary. You do not even have to think about the expectations and so on. You just look at Vk, it just becomes unbounded, right. Not in the deterministic in the sense not as much as a deterministic signal would go, but it will definitely become unbounded. Now, it turns out that although this process is stationary in the sense of the theorem that we have given there, non-stationary in the sense of theorem that I have given, it can still be given a stationary representation. What we meant by Vk running off is, if you were to plot Vk versus time, you would see some kind of growth like this, right. From that viewpoint, it is non-stationary. It turns out that I can give a stationary representation to this process if I am going to budge a bit on this notion of causality. We have actually said earlier, when we said h of n is alpha 1 lambda 1 power n, alpha lambda 1 satisfying your usual condition, but importantly we said n greater than or equal to 0. Although we have not stated, it was implicitly assumed that h is 0 for negative times, correct. If I am willing to sacrifice that assumption, if I am willing to let non-causality creep into my model, then I can give a stationary representation to this seemingly non-stationary process in the causal world. That is strange, is not it? In the causal world, this process is non-stationary. What we mean by causal world is when the impulse response is 0 at negative times. But when I look at it backwards, in other words, you can rewrite this equation as Vk minus 1 equals, how do you write this? Minus 0.5 Vk, assume some E tilde k, okay, it would be minus 0.5 ek, sorry, there would be no minus here, 0.5 ek minus 0.5 ek, but we can absorb that minus 0.5 into ek and create a new sequence and think of this as E tilde. E tilde is nothing but minus 0.5 E. When if I were to give you this model, the first thing you observe, it's non-causal, right, but it is stationary. So, an explosive series can be given a stationary representation, and that is the point here. Okay. There is a connection between causality and stationarity when it comes to autoregressive models, and that is the example that I have worked out more in a symbolic fashion on the screen for you, where I, instead of 0.5 I have D1, right. So, the point here is a non-stationary causal or an explosive causal model or causal series can be given a stationary representation, but with non-causality. Is this model of any use to me? What do you think? Is it of any use to me in forecasting? It is of no use. I mean, it is just for my fun, it is just to confuse you further. But having said that, there are a set of problems where this kind of model is actually useful in what is known as backcasting. Have you heard of backcasting? We have always thought of forecasting, right? But there is something called backcasting. When would be backcasting useful? Any idea? Any application? Sorry? When forecasting is not giving me the right thing, turn to backcasting. Right? Turn your back onto it. Correct. Right. Very good. So, if you want to actually extend that, it is not exactly that. When I have missing observations, for example, right, and I have data, historical data, I can use backcasting to recover the missing data. So, it is not that these non-causal models are of no interest at all. Now, you have to change your opinion. The non-causal models are indeed useful many times. In fact, many a times we use the non-causal models. In estimation, there are three different problems. One is that of prediction, which is forecasting. Then there is that of filtering. What is the difference between prediction and filtering? Prediction is given all the information up to k, I would like to estimate the signal at k plus 1, k plus 2 and so on, common sense thing. Filtering is I am given all the information up to k, meaning measurements up to k, and I want to get an estimate of the truth at k. Just because I am given measurements, I am not given the truth. Remember, there is always going to be this error. And I will give you a very simple example that you can relate to. But let me discuss the third problem. The third problem is that of smoothing. What is smoothing? Smoothing is is the exercise of obtaining an estimate of the truth at k using the information to the left and right. That means you would use k plus 1, k minus 1, or maybe even more. Essentially, you look to the right and to the left and say, this is where I am. Right? Sometimes when you get up from sleep, deep sleep, you do not know where you are. It happens to almost everyone. So, you are dazed really. If you look to one side, you are still not able to gauge where you are. But you look around and say, okay, now I know my GPS position. Okay, my brain has figured out what my coordinates are. A more practical example is when we go and watch movies where actually fans volume is louder typically than the movie volume, you are trying to actually get an idea of what this dialogue is at that moment, or you have to go out and maybe get a popcorn or something to eat and you come back. With Bollywood movies, it is excellent. Actually, you should be really happy with Bollywood movies because there is such an element of predictability in Bollywood movies that you have It's the problem is with Hollywood movies. First of all, with Hollywood movies, you have to really shut off everything. You can't even talk to the person who came with you. You can't pay attention to your child, nothing. Because that guy is talking so silently as is, there won't be enough light. Right? On top of it, they would be whispering and you're wondering what on earth is going on. And one has to watch 10 times and it's unpredictable and so on. Depends. If it's a James Bond movie, it's predictable. But by and large, Hollywood movies have a problem. Bollywood movies, you should be really thankful that it's predictable, in the sense that even if you miss a few minutes, you can actually recover that based on what you heard before you left the hall and what you heard after you entered the hall. That is smoothing. Many times, seriously, you think that actually these problems are alien. No, they are not. We are using it every day. The only difference is we are looking at a formalization of those concepts, that is all. So, human brain has been doing all of this for ages, since times immemorial. Many a times you see in the movie theatre, the movie dialogue being predicted by the fan. Like, you know, agar tune maa ka doodh piya hai to aaja. The standard dialogue. Right? But maybe the dialogue has changed now, so the model has to be updated. That's the only difference. That dialogue probably, that prediction applies to a class of movies until 70s or probably 80s. But beyond that, the way the hero calls out the villain, the model has changed. So if you have seen enough movies, then your model is updated. And then you use a model switching depending on the era in which the movie was made and you predict. That is prediction. Based on what you have heard, you are predicting what's going to happen. Filtering is you have heard it, but there are so many fans shouting around you that you are not able to get the clear picture. Yet based on what you have heard already and whatever little you have heard, you are trying to figure out what the exact dialogue is. So the person sitting next to you, maybe your family member, is asking you, what is it that they said? Then you immediately reconstruct and say, yeah, this is what perhaps it meant. And then you confirm that when as the movie goes on, yes, I was right. Or maybe you correct it. You say, no, no, that's what actually he said. But it is that correlation that is allowing you to make that. Imagine if your movie was white noise. Seriously, there would be no fun at all. You have to sit really tight. So you should really thank, maybe one of you can send a thank you mail to the filmmaker saying that please do make movies that have a high element of correlation in them. That is, you take the ACF, there is a very slow decay. Okay. So anyway, coming back to the point, non-causal models are useful for backcasting. Right. Subject is, if you establish connections with real life, it's real fun. So henceforth, we will work only with causal models, and it's assumed, in fact in many texts that's what is also stated, the moment we say causal AR model, it's assumed it's stationary. You don't have to, again, one doesn't have to explicitly state that it is stationary, unless it is stated explicitly, but by default a causal autoregressive model implies stationary model. If it is not, then it would be non-causal. I mean, you can build a non-causal stationary representation. So in a sense, it is always possible to construct a stationary autoregressive representation. It's a matter of whether you are willing to tolerate non-causality. If you are not, then you will work with only causal models, which is what we are going to work with. Nice. So that now settles the stationarity issue of autoregressive models. Now we move on quickly to the ACF. We have seen this before. We know that the ACF has an exponential decay, and we have also seen learned how to derive the ACF for an autoregressive process by writing the Yule-walker equations, and we are just going to go over that as a refresher. We know that the autocovariance function of an autoregressive process satisfies the same difference equation as the process itself, and when you write down those equations, you are led to this bunch of equations known as Yule-walker equations. Generally, we write an equation separately at lag 0, and where the right hand side you have sigma square E, and then at all non-negative lags the right hand side is 0 and it is just a difference equation form, pretty much looking like the process itself. So now from the theory of difference equations, as I have even said earlier, you can write a generic solution. I am assuming for just the sake of discussion that the roots of the characteristic equation. Now, you see the ACF has the same characteristic equation, the difference equations for ACF has the same characteristic equation as that of the process. So, the roots are the same. The only difference is H, the constants that appear in H when you have sigma alpha i's and so on, those alpha i's are different now. So, that is why I have betas now, but otherwise the form of the solution does not change. What does it tell us now? It reveals us something very nice. Earlier we said parameterization of impulse response coefficients according to the power law implies autoregressive form of a certain order. Now, we learn another thing. By parameterizing the impulse response coefficients in a particular way, we are also implying that, what are we implying now? That the ACF also has a certain parameterization. I go to that statement and I will come back to the Yule-walker equation. I just want to bring up that statement on the screen and then we will come back and talk about the PACF and so on. Okay. So, parameterizing the impulse response coefficients assumes is equivalent to parameterizing the autocorrelation function itself. Whether you are doing it explicitly or not, that is a consequence. That means, when you look at the ACF of a series and you are fitting an autoregressive model, you are implicitly saying the ACF actually decays according to a certain law. And now you can also see this for the MA model as well. In the MA model, we assume that the impulse response coefficients die down abruptly after time instant m. That there also that assumption translated to the same situation, ACF dies down exactly after lag m. So, whatever I did on the impulse response coefficient is more or less the same on ACF as well. So, whether you assume parameterization of impulse response coefficients or parameterization of ACF or a particular model, they are all equivalent. How, which do you consider as a starting point is your choice. You can start from one and then end up with the others. And going further, we know that the spectral density is related to the autocorrelation function through the Fourier transform. And by virtue of that relation, parameterizing the ACF also amounts to parameterizing the spectral density. See, parameterizing means what? That we are actually expressing the function in terms of those parameters. That is what parameterization means. So, in effect, your AR models are actually parameterized linear models for linear random processes, and so are moving average models, but in the moving average model there is no parameter per se. All you are assuming that is that the impulse response coefficients go to 0 or the ACF goes to 0 or that the spectral density has a certain form and so on. Of course, we have not talked about spectral density, but it is waiting for us in the next room. So, we will board that wagon pretty soon. So, that is the point you have to remember. The moving average, whether it is moving average or autoregressive model, whatever you do, there are two other consequences. One is parameterizing the impulse response and the other is the parameterization of the ACF, and the third one is of course parameterization of spectral density. Instead of remembering it as parameterization, you can think of it that you are this way, you are assuming a certain shape and a mathematical equation for that shape, either for the IR coefficients or the ACF or the spectral density. Okay, so that is something that you should remember. Let us get back to the ACF part. So, we know we have seen this Yule-walker equations before, and I am just showing you some sample calculations as to how you can solve this Yule-walker equations for getting your ACF. So, for example, for an AR2 process, if you solve the Yule-walker equations, this would be the expressions for autocovariances at lag 0, 1 and 2. Practically the use of Yule-walker equations, they are more popular for estimating model parameters, and we have talked about this. You can use it for two purposes, either given model I can calculate the theoretical ACF as I have done right now for you, or given ACF I can calculate the model parameters. And these are the equations that you would use for an AR2 process. For example, if I am given the ACF, I would use these two equations to solve for D1 and D2. Now, notice that for an ARP process, typically we write P plus 1 equations, right. What we have used here to solve for D1 and D2 are only the equations for non-negative lags, sorry, for non-zero lags, positive lags, let me put it that way. In other words, let me go back to these equations that we had written here. Sorry. So, here if you look at it, there are 3 equations. I have used only the bottom 2 equations for getting my D1 and D2, because I can decouple the problem of estimating sigma square E and the parameters. I would like to decouple, right, and then go back and substitute this into the top equation to get an estimate of sigma square E. That is the usual procedure. So, the Yule-walker equations gives us nicely a set of linear equations. That is the beauty. With autoregressive models, that is the beauty, that you will always, you can end up with a bunch of linear equations depending on the optimizer that you use. If you use the Yule-walker method, you will end up with a bunch of linear equations and easily solve for the parameters. This was not the case for moving average models. Why do I keep pointing out these differences between these 2 models? Because in practice one has to make a decision at the time of modeling. If I give you data and you have to make a decision on which model to choose, you have to be very well versed with the features of all these models in terms of how easy it is to estimate the parameters. What are the ACF signatures of this? Generally, if nothing is specified in terms of which model to prefer, there are certain criteria, and I will talk about it in tomorrow's class when we talk about which models to choose, but it is common sense, the ease of estimation will dictate which model I should choose. So, between AR and MA models, which are easier to estimate? Autoregressive models, because I have a bunch of linear equations, right. Now, the only thing that I have to guarantee is this bunch of linear equations that I am solving will give me estimates that are going to satisfy the stationarity requirement. Whereas with the MA model there was no issue, but there is another issue with the MA model. Apart from solving nonlinear equations, I have to choose the one that is invertible, but I am guaranteed there will always be an invertible solution, provided those conditions are satisfied and so on. So, there are pros and cons of each of this, but the fact is for autoregressive models the equations that you solve are linear, and usually this is a procedure that is used, and that is why in many packages, many software packages including R, there is a separate routine for estimating AR models. There is a routine for estimating ARIMA models, which is ARIMA in R, but there is a separate routine for estimating AR models, which is AR. And within that AR, if you just go home and look up the help on AR, you will see there are a number of methods listed, YW, LS and MCOV, modified covariance or Berg's method and so on. YW stands for Yule-walker's method. It essentially uses these equations, right, and default is Yule-walker. It is very easy to estimate. We will show later on that the least squares method also gives us a bunch of linear equations pretty much like the Yule-walker equations, almost. For large samples it does not matter actually, for large sample sizes both are going to give you same results. Berg's method is different. The big advantage of Berg's method of estimating AR models is it guarantees stationary solution. Okay, that was way back in mid 70s that Berg proposed. So, this is a general set of equations that you see for an ARP process, and this is how you estimate your D, and in practice you would replace the variance, the autocovariances that you see in these matrices and vectors with the respective estimates. That is a method of moments approach. When we meet tomorrow, we will talk about very briefly the order of AR processes, determining the order, and then also talk about the equivalence between AR and MA and talk about ARMA models as well. Okay.